PM Research design for the flywheel uses a keyway with a set screw in the flywheel to hold it securely to the crankshaft. Perfectly reasonable design, but I thought I'd do something a bit different just for fun to give me an opportunity to turn an accurate taper. So I designed this split collar. This is a very typical design of a split collar used to secure pulleys and things like that. And this will give me a chance to try out Mr. Crispin and a Joe Pye technique for accurately setting the compound slide to machine the taper. And so that's what this video is about. Thanks for joining me, and hope you enjoy it. Going to start by just cleaning up the end of this steel and doing a very light cut on the outside. This material is basically to size, so I'm just going to clean it up. Alright, that's spot on. I'm going to turn this diameter down off camera. This triangle represents what we're trying to do. Now look, there's my turning tool. This leg of the triangle is the distance that's going to be traversed by the compound slide. This represents the axis of the cross slide, and this represents the z-axis of the saddle, which we're not concerned about right now. I'm going to be turning this taper using the compound slide, so I've got it set approximately at 5 degrees according to the markings on the slide. But of course those are not accurate enough to be able to repeatedly set it up. So here's the idea, is that we move the compound slide a known distance using the dial, known distance of 1 inch. We can use a dial test indicator to touch off on the tailstock at this end. So then we traverse this 1 inch, then I can use the cross slide to move in until the test indicator gives the same reading, and then we will know what this distance is from the digital readout. So if we do a little bit of trigonometry here, we can understand what that distance needs to be, and we can alter and rotate the compound slide as needed. Now, in terms of the maths that we need to know, we're talking about using the sine here. On the triangle, we've got our angle, we've got the opposite leg, the hypotenuse, and the adjacent leg. Adjacent leg doesn't matter, so we're going to be working with the hypotenuse and the opposite, and the formula we need is the sine of the angle equals the opposite divided by the hypotenuse. So if we rearrange that a bit and solve for the opposite, we know that it's the hypotenuse times the sine of the angle. So we know we're trying to get 5 degrees. So in our sine tables, we looked that up, which is 0.08716. And then we perform the calculation of 1 times 0.08716. And after we crunch that for a couple of hours, we round it up a little bit, we find out that the opposite needs to be 0.0872 inches, which is 2.215 millimeters. So we can traverse this with the compound, move in, and then see what we get on our digital readout, and then we can adjust the angle, repeat this until we get precisely this distance, and then we'll know that the compound is set up to 5 degrees very accurately. So we'll go over to the lathe and give that a go. At the lathe now, I've got the compound set up at approximately 5 degrees using the rotary dial numbers here. Have a 5/10 DTI, and so using Joe Pye's method here, I'm going to traverse the cross slide and touch off on the tailstock quill, bring it to a known position. And keep this in focus. I have the compound slide set at a 0 position. Now I'll bring the cross slide in and bring the needle to a known position on the DTI. There we are. Zero the DRO. Now I can move 1 inch on the compound slide. Now traverse the cross slide. Bring it back to the same 0 position. Oops. A little jerky. Now if we look at the DRO readout, what you have to remember is I'm in diameter mode. So that means the DRO is automatically compensating for that travel. The travel of the cross slide is traveling on the radius of the part. So the DRO doubles the reading so that I have a diameter readout. So I have to half that number, which I can do using the DRO. And so that now tells me that I've moved 0.0872 inches across, which is exactly the number that I was shooting for. Now if that, and I knew I was going to do that because I already spent some time setting up the angle so as not to waste your time on the video. If I wasn't precisely located, then we would simply slacken off the locking screws on the compound and just gently tap one side or the other, watching the needle on the DTI, and gradually adjust it in and then repeat these measurements. But now that we know we've got 0.0872 inches across the cross slide for every 1 inch on the compound, we know this is set at precisely 5 degrees. So first order of events is to finish turning this diameter, and this has to end up at 0.784 inches and 3/8 long. So let's 0 this. And we'll do an initial setting here. As I recall, I had this at about 1 inches. So we'll set that up now, but I'll take a cut and then establish what it actually is. So we'll just do a light 20 thou cut. 0.979. Now I've got a real reading, live reading of the diameter. Okay, I'm going to put a bit of coolant on. .784 on the money. Now that the digital readout is set accurately relative to the tip of the tool, I kept my compound slide dial at the 0 position, so now I know I can traverse using the compound slide and bring it back to the same position, and I can traverse with the cross slide and get to the diameter that I need at the end of the taper. So I think that's how it's going to work. I've never done this before, to be honest with you, so let's see how it goes. This is 0.784. On the diameter, and that's the 0 point of the start of the part, which you can't see because it's behind the tool post. Let me see what I can do about that. Alright, another try. I'm going to use WD-40 to lube this to keep the tool bit in view, just so we can see what's going on. So as you can see, I've got the tool bit right at the 0 point, essentially, that edge. I'm going to take it back 1/10. And traverse the cross slide. Looking for 0.725 at this point. do next? I think I'll put the undercut in here. I'm a big fan of undercuts in the right place. That's a 0.626. That's a 625, and look at that. Lovely. Well, I'm going to leave it there for today because I seem to be making a lot of mistakes.